On March 11, 2011, the ocean floor off the coast of Japan moved 50 meters in 3 minutes. What came out of that motion was a wall of black water 40 meters tall, moving faster than a car on a highway, and it erased entire towns before anyone could reach higher ground. Japan's answer was to spend $12 billion building a wall 400 kilometers long to make sure it never happens again this way. This is Japan's post-tsunami seawall, the largest coastal defense system ever built by a single country. 400 kilometers of concrete, steel, and buried infrastructure running along the Tohoku coastline. 440 separate construction contracts running simultaneously. 443 automated floodgates wired into a single command network, and a wall so massive that most people outside Japan have never even heard it exists. Here's the part that sounds backwards. You'd think the goal of a wall like this is simply to stop the next tsunami cold, wherever it hits. It isn't. Engineers openly acknowledge this wall was never designed to stop a wave on the scale of what hit in 2011. That wave was simply too large, too fast, and too destructive for any affordable coastal structure to fully block. Instead, the wall is designed to blunt smaller, more frequent tsunamis entirely, and to buy critical extra minutes of warning and slower flooding during a wave as catastrophic as the one that struck in 2011, giving people time to reach higher ground that the original, much smaller seawalls never gave them. The scale of what happened on March 11, 2011 is difficult to overstate. A magnitude 9 earthquake ruptured roughly 500 kilometers of ocean floor off Japan's northeastern coast, displacing an enormous volume of seawater and sending it racing toward shore as a tsunami that crossed open ocean and reached the coastline in about 30 minutes. This wasn't a single wave in the way people picture waves at a beach. It was a moving wall of water, in places measured at close to 40 meters high, carrying with it entire buildings, vehicles, and boats. And it simply did not stop at the shoreline the way ordinary waves do. Roughly 90% of Japan's existing seawalls along that stretch of coast failed in that single hour. Some of them didn't fail from the front, the direction engineers had spent decades designing against. Water topped the wall entirely, then eroded the unprotected back face on the way down. And once that back face gave way, the foundation underneath went with it. Japan's largest breakwater at the time, a structure that had cost over $1.5 billion to build, was destroyed in seconds by exactly this failure mode. In town after town along the coast, one mayor's decision to build a taller than required wall years earlier became the reason roughly 3,000 people in that single community survived, while neighboring towns with lower, more conventional walls lost everything. That contrast becomes the blueprint for everything that follows. If a taller wall saved one town, then a taller, smarter, more thoroughly engineered wall along the entire coastline becomes the national response. But designing a wall to survive an event on this scale means starting from a completely different set of assumptions than the walls it's replacing. Before a single new stone gets placed, engineers spend months modeling wave behavior along every kilometer of coastline, running each section of the planned wall through computer simulations roughly 200 times before construction on that section is ever approved. Wall height ends up varying constantly along the 400-kilometer route, rising taller on exposed headlands that catch the worst of open ocean wave energy, and dropping lower in sheltered bays, where the surrounding geography already blunts incoming waves naturally. None of it is uniform, because the coastline itself was never uniform to begin with. 440 separate construction teams eventually get mobilized to build this wall simultaneously, because a 400-kilometer structure built sequentially by a single crew would take decades rather than years. Coordinating that many independent teams creates its own risk. If even one contractor goes bankrupt or falls badly behind schedule mid-project, a literal gap opens in the coastal defense system at exactly the section that contractor was responsible for. Zero tolerance gets applied to that risk, with oversight structured specifically to catch struggling contractors early enough to intervene before a section of coastline is left exposed. Before construction starts at any given site, survey ships drill core samples into the seabed, because the ground beneath this wall is anything but consistent. Engineers eventually classified the foundation conditions along the route into three broad categories: soft clay, dense sand, and hard rock, each one requiring an entirely different foundation approach before any visible wall structure can go in above it. The first construction task at nearly every site isn't building anything new at all. It's demolishing what's left of the seawalls that failed in 2011, then studying exactly how and why each one failed before designing its replacement. Clearing the land side of the site brings its own complications long before the wall itself starts rising. Coastal pine forests that once buffered the shoreline get cleared where the new alignment requires it, and erosion control matting has to follow the bulldozers within minutes of clearing, since exposed soil along this coast erodes fast enough that even a short delay can undo days of preparation work. Along stretches of clay-based coastline, the ground is soft enough that ordinary construction machinery simply cannot cross it without sinking. Steel road plates get laid down ahead of every machine specifically to spread its weight out across a wider footprint, letting equipment effectively float across ground that would otherwise swallow its wheels or tracks whole. Some of the most difficult work happens entirely out of sight, below the waterline. In the active surf zone, divers guide multi-ton boulders into position on the seabed by hand, working inside a tidal window that gives crews as little as 4 hours of usable working time each day, in the very same ocean that had just demonstrated what it's capable of. Engineers monitoring the underwater progress can't see what's actually happening below the surface. They rely entirely on sonar data, trusting instruments to confirm that boulders are landing where the design calls for them, since visibility in the surf zone makes direct observation impossible. Between the boulders and the fill material that eventually forms the wall's core, a filter layer goes in specifically to stop fine soil particles from migrating out through the gaps in the rubble over time. Miss that layer or install it incorrectly, and the wall slowly bleeds its own foundation away underwater, invisibly, for years, long before anyone notices a structural problem on the surface. Once the underwater rubble mound finally breaks the surface after weeks of work, a geotextile membrane goes down across it, again to stop fine particles from washing away, and compaction rollers work the surface until it can hold a slope angle of roughly 1 to 1.5. Steep enough that boulders won't slide, shallow enough that incoming waves actually break against it rather than slamming into it directly. Above the waterline, the wall itself starts taking shape as a layered structure with multiple separate jobs built into a single cross-section. Sheet piles get driven 10 meters down into the seabed specifically to protect the toe of the wall, the section most vulnerable to the backwash of a retreating wave, rather than the initial incoming wave itself. Engineers treat that retreating backwash as more dangerous than the wave crashing in, since it's the outgoing water that scours sand and soil out from underneath the foundation, undermining a wall from below in a way the incoming wave alone rarely manages. Thousands of massive precast concrete panels, some weighing 7 tons apiece, get manufactured off-site and trucked in to face the wall's exterior. Every panel gets tapped by hand before it leaves the production yard, and a technician listens for the sound. A solid ring means good, uncompacted concrete throughout. A hollow sound means a void somewhere inside the panel, and that panel gets sent straight to the crusher, regardless of how close the project is running to deadline. Because a single defective panel installed into a tsunami wall isn't a cosmetic problem. It's a structural weak point built permanently into critical infrastructure. Because the coastline curves constantly and the original wall design assumed mostly straight sections, engineers eventually have to develop dozens of unique panel shapes, computer-designed and machined specifically to close the gaps that would otherwise open along curved bays where straight, standard panels simply wouldn't fit flush against each other. Rubber water stop seals get built into every joint between panels, engineered to swell when wet, meaning the larger and more powerful the wave pressing against a joint, the tighter that joint seals itself in response, rather than failing under exactly the load it was built to resist. Above the main wall face, a crown wall caps the structure, angled outward at roughly 10 degrees from vertical, specifically to throw overtopping water back out to sea, rather than letting it crash down onto the landward side, where it would otherwise erode the unprotected back face the same way it did in 2011. Hairpin bars tie that crown wall directly into the panels below it, turning what could have been a series of individually stacked concrete pieces into one single, continuously connected structure, capable of acting as a unit under load, rather than as isolated segments that could shift independently. The backside of the wall, facing land, gets just as much engineering attention as the ocean-facing front, because engineers now understand from direct experience that back-face failure, not frontal failure, was what actually destroyed most of the walls that came down in 2011. A landward drainage system gets built in specifically to give overtopping water somewhere safe to go if it does eventually spill over the crown wall during an especially large event, rather than letting it pool and erode the unprotected earth behind the structure. Offshore, ahead of the main wall itself, engineers add a second and sometimes third line of defense. Concrete tetrapod armor units, some weighing over 30 tons apiece, get placed, not with precision, but essentially dropped into the water, where their interlocking four-legged shape naturally finds a stable resting position among neighboring tetrapods, without needing to be positioned exactly. The gaps between tetrapods aren't a flaw in the design, they're the entire mechanism. Wave energy passes through those gaps and dissipates gradually, rather than slamming directly into a single solid wall face all at once. Further offshore still, submerged breakwaters sit entirely underwater, designed specifically to trip and break a wave's energy hundreds of meters before it ever reaches the main coastal wall, forcing the ocean to exhaust some of its power well before the fight that actually matters. Woven through the entire 400-kilometer system are 443 floodgates. Positioned anywhere, a river, a road, or a harbor entrance needs to stay open for daily use, but sealed instantly the moment a tsunami warning is issued. Seismic sensors trigger automatic gate closure the instant a qualifying earthquake is detected, with no human authorization required in the loop, because the entire window between an earthquake and a tsunami reaching shore can be as short as a few minutes. Engineers designed the closure sequence around a target of roughly 70 seconds, from alarm to fully sealed. The estimated margin available before a wave could realistically reach the coast in the most vulnerable sections of the system. Every one of those 443 gates ties back into a single centralized command network, monitored from one control room capable of watching every sensor and every gate status simultaneously. On March 11th anniversaries, the entire system runs a full closure drill, testing the actual coordinated response rather than assuming individual components will simply work when called upon during a real event. Since the system's completion, it has already been tested under conditions its designers specifically hoped it would never have to face again so soon. A magnitude 7.4 earthquake struck the region directly, triggering automatic closure of all 443 gates simultaneously. Engineers monitoring strain gauges across the wall afterward reported 0 cracks and 0 shifted tetrapods, a result considered extraordinary given the seismic force involved, and a strong signal that the redesigned system is behaving exactly as its post-2011 engineering intended. Independent monitoring continues indefinitely, rather than stopping once construction wraps. Sensors embedded throughout the wall track settlement and structural movement daily, and engineers have already documented roughly 14 millimeters of differential settlement across the full 400 kilometers of coastline in the years since completion, a figure considered remarkably small given the scale, the variable foundation conditions, and the sheer length of the structure involved. What was once open coastline, and in places a wall barely tall enough to matter, is now a 400-kilometer structure engineered in layers. Sheet piles below, custom concrete panels along the face, an angled crown wall on top, tetrapods and submerged breakwaters offshore, and hundreds of automated floodgates tied into a single network, watching the coast around the clock. None of it promises to stop a wave on the scale of what happened in 2011 outright. All of it exists so that the next time the ocean floor moves, the towns behind this wall get more time, and a coastline that gets a real chance to still be standing on the other side of it. Life along the coast has adjusted to the wall's presence in ways the original engineers didn't necessarily plan for, but have come to accept as part of its legacy. In places, the wall now blocks the ocean view from homes that once looked directly out at the water, a trade-off some residents accept without complaint, and others still argue about more than a decade after construction began. Staircases built into the wall at regular intervals aren't scenic overlooks. They're evacuation routes, designed using crowd flow research so that residents can clear the wall and reach higher ground quickly during a real event, rather than bottlenecking at a handful of access points. On ordinary days, with no earthquake and no warning sounding, those same staircases and the promenade running along the top of the wall have simply become part of daily life for the towns it protects. People walking dogs, running in the morning, cycling the same stretch of concrete that exists first and foremost to save their lives. If you want to see which megastructure we take apart next, hit subscribe. We're just getting started.